And lastly today, a slightly easier waves topic to finish the content, refraction. If a light ray goes from one material to another material, and it enters at 90 degrees to the surface of the second material, then it'll just keep on going in a straight line. But if the light ray enters at an angle to the perpendicular there, and the new material has a different refractive index to the first one, then the light ray is going to bend, and that's what refraction is. It's happening because one side of the wavefront is entering the new material first, and it's either speeding up or slowing down compared to the rest of the wavelength that is still outside in the first material. Snell's law tells us the relationship between the refractive indices of the two materials and the angles to the perpendicular, the angles to the normal in the first material and the second material. The refractive index of a vacuum is exactly 1, and the refractive index of air is very, very close to 1. So in your A level, you're just going to use n equals 1 for air. Other materials have larger values of n. And you might ask what n actually is. Well, the n of a material is equal to the ratio of the speed of light in that material compared to the speed of light in a vacuum. And that is obviously why you get 1 there if the material is in fact a vacuum. In the diagram I've drawn here, you can see that the light ray bends away from the normal. So theta 2 is bigger than theta 1. And so that means that N1 must be bigger than N2. So this light ray is going from a material with a larger N to a material with a smaller N. So for example, water to air or glass to air or something like that. When the light ray is moving from a material with a bigger N to a material with a smaller N, you can see that if theta 1 gets bigger and bigger, then theta 2 will also get bigger and bigger, and you'll reach the point where theta 1 will cause a theta 2 of 90 degrees, and whatever theta 1 is at that point, that is called the critical angle for the material. Sorry, I should say for the boundary. So that's the situation we've got drawn here. Now, when theta 2 is 90 degrees, theta 1 is called the critical angle. That's what we've just said. And then, if we make theta 1 even bigger than the critical angle, well, the light ray is now going to have to go more than 90 degrees, and that means it's come back into the first material. Now, what you've got at the boundary is reflection. And because all of the ray is reflected back in, it's called total internal reflection. And because it's reflection, of course, this angle has to now be equal to that angle. This is now an example of reflection. Okay, and so here's a refraction question to finish today. Now this diagram's pretty confusing looking, so it's a bit tricky to find your way through this one, but just remember, first of all, identify where is the boundary, where is the refraction happening. So if we're interested in angle alpha, we're interested in the refraction that's happening here. Right then, so where are our two materials? Well, the light ray's coming here, so this is going to be material 1 and this is going to be material 2. Okay, so our first material is the transparent substance, and the angle to the normal is 65 degrees, which we get from geometry. And then the second material is air, and then the angle to the normal is that angle there. So the first thing we need to do is work out what that angle there is. And if you substitute these values in here and carefully rearrange, you'll get that theta 2 is 81 degrees. And so that means, again, a little bit of geometry there, that alpha must be 9 degrees. Now, although we appear to have only one significant figure in that answer, we never round to one sig fig apart from absolute uncertainties. So I'm going to give my answer as 9.0 degrees there. And now, to find angle theta, we've got a whole lot of geometry going on this one. So if that's theta there, then that means that this here is also theta. And so it's this angle to the normal that we need this time. And so this is nearly labelled at theta 2. That's theta 1. This is our first material. And then there's where our refraction's happening. So first material, second material this time. First material, second material. So here are our numbers for the next calculation. There's theta 1, angle to the normal, and there's theta 2, angle to the normal, material 1, material 2. Put all your numbers in and theta 1 will come out as 36 degrees to two significant figures. And then don't forget that the angle they've actually asked us for is that one. So 90 minus theta 1 is the angle that they want.